Hello.
Hi.
Good. How are you?
I'm good, thank you.
That's good. I have prepared a formula sheet for you. Do you want to have a look? Or perhaps
Okay.
I sent it to you first.
Okay.
I will. Second. Okay. Sent. Yeah, it's a PDF file. It's just 2 pages. How many pages do you have? 10, 5? The formula sheet.
Mine's double-sided.
Yeah.
And it is I'll just count the single pages. 1, 2, 3.
More than
4,
10?
6, 7. I have 7, like altogether it's 7.
All right. I've sent it to you now. Just probably we'll discuss this because this is based on what we have done for the past few weeks, and it was tailor-made for you. So we will put almost all formulas, concept, and units.
Yeah.
Have you seen that?
Yeah, I got it up now.
Good. So we can repeatedly use that if any issues, or for example, you say, well, your teacher asked for more or less, and we can modify that formula before examination. You see, that is what I did. When I was a student, I just prepared this single sheet or 2. And because at the end of the day, you are not supposed to carry the book, okay? It's just, single pages formula. So just look at my format is different from you, but I will explain to you the. Of course, first part is to do with motion. Can you see that keyword motion?
Yeah.
So every time you're dealing with motion, the acceleration, displacement, velocity, acceleration, you go to that part, okay? And also got a number, you see. So we can communicate. For example, you say, hey, which formula should I use as number 3? Okay, that would be quicker. The second part is about the force. I understand you didn't at school, you didn't spend too much about the force, but you do know that the net force equal to A divided by M, right? That's okay, right? That's all right. And then something to the energy. Of course, I didn't put the momentum, which is related. When you talk about kinetic energy, immediately you will think about momentum as well. And then a little bit of thermal here. I noticed last session we are dealing with the change in internal energy equal to the sum of the heat plus work. So here we are. Here's a formula for you. So next time, you see, I put all quantities with the joule together. The unit is joule together, can you see?
Yeah.
Energy, potential energy, inertial energy, heat, work, okay? And also nuclear binding energy. Okay, the last shaded area will be the nuclear. So in the nuclear section, and we got the binding energy formula here. So you basically have to work out the mass defect. I listed the mass defect formula separately. Can you see number 17? Can you look at number 17? In number 17 this is a formula for calculating mass defect. Now there are 2 different formulas. The first one we're dealing with a single nuclear. Okay, so you completely separate the nuclei into proton and neutron. Okay, that is how we calculate the nuclear energy stored in the one nucleus. The second one is just calculate the sum of the mass before and after reaction. Okay, so this is just a short note. For example, Mi or the initial net mass could be involve 2 parts. You agree? So sometimes you have, for example, during the fusion, you have to combine the 2 hydrogens isotope together to form the helium, right? So in that case, Mi will be the sum of two hydrogen, okay? The final one will be after that reaction. That's called the final. In this case, in this particular reaction, it's just the mass of helium, that's all. Half-life time, yes, that is, we can put this formula here for you. So N equal to NO, can you see that? 18, formula 18. And that is a formula you can use. Depending on how many half-life time you have waited, so that can be calculated by using the total time or waiting divided by the half-time. Then you obtain the number of how many half-life time. That is N. That next one is oscillation. So basically the amplitude, period are important concept here, right? And this the concept and the unit. Can you see? I not only use the unit, but also put the full name for unit as well as their initials. For example, Hertz. Now Hertz, that's how to write. HZ is how to, that's initial for Hertz, right? And last, of course, is a wave. Okay, the next will be the wave. So we spend a lot of time to dealing with wave. So basically, if you look at formula 25, we have to use this repeatedly. So the speed of wave will equal to the product of wavelength and frequency. The next shared one is from 26 to 28 is for electricity. Okay, so that is easy for you to look. Okay. So you just look for the keywords and you go to that particular section, then you should be able to find the formula and the definition as well as units, okay? If you go to next page, another one is about the refraction. Perhaps you haven't studied that, so I just put the 29 there, just in case if you jump to the next chapter, which dealing with the wave, okay? It's called refraction. Second page is just, you know, the frequently used constants, like the speed of light, the gravitational acceleration, and more important, you see, the charge of electron in the unit of coulomb is a small number. And I also included the mass for proton and neutron in both kilogram as well as atomic mass unit. And also I included the mass for electron, which just tell you that it's just very small. It's just the mass of proton divided by 2000. This section, and that's the notation for the atom, I think is important. And no matter what atom or what nucleus is, you should be able to interpret that two numbers in terms of your number of electron, number of proton, number of neutron. And more importantly, you can see, because why do we call A is a atomic mass number? Because if you use just use the U, that's the atomic mass unit, every time you give an unknown atom or nuclei, from its A, you can just estimate the approximately what their mass is. You just A times that unit. Can you see that? So that is not, can you see that's the mass of any atom equal to approximately A times U, okay? Mm-hmm. I hope that will help you to simplify these contents, okay? Of course, this table I put it here because as I noticed, we often use this concept here. For example, there are the elementary particles we encounter so far, such as proton, neutron, electron, and positron. Okay, positron is not naturally exist. They just come in the beta decay. Photon and the helium nuclei, put them together. So together with the electric charge. So I think at the beginning some have trouble with counting the charge, right? Now you have no problem. You just count. You just count how many the positive guys there, how many neutral guys there, how many, or sometimes if you don't. If you study nuclear, forget about electron. But from time to time, electron come from nuclear, as it happened in the beta decay. Okay. Last, I think, this is just a summation of the summary of the different conservation law. And you see, physicists dealing with the change in the nature, that they have the assumption that no matter what happens, at least these few quantity will remain invariant or constants. including total energy, including total momentum, including total mass number, including the total electrical charge. The last is you have to use Einstein's idea, a little bit abstract. Einstein said, well, mass cannot be conserved because it got a mass defect, right? However, if you treat the mass as equivalent to the energy, everything can be explained. So that is the last one, is called energy mass conservation law. Okay? Only question? No question, we can go
I
to
don't
problem
think
solve.
so.
Okay, so you can put this, you can print out whatever, you put it there, so we can repeatedly use this to see we covered almost all questions, okay? Shall we go to revision 9, right?
Oh, I have another one.
We got number now. Do you want to continue number 9 or new one? A new one.
I handed in number 9.
Oh, okay. You told me you have done. So you want to send me number 10?
Yeah, I'm just saving it now so I can send it.
I hope you will find this problem solving fun, you see, because they just counting. Sometimes they just counting. There are not many. Of course, sometimes you have dealing with number with many decimals. That is a bit nuisance. it just want to demonstrate small change in the mass will convert into large quantity, large amount of energy. That is the idea they're trying to persuade the students to understand. That's why every digit, every decimal count, okay, matter. Okay,
I sent it.
Look for your email to see the number 10 revision. Okay, I got your number 10 now. Open it. Number 10. Yep, that's one. I download number 10. Did you try any? Have you, or just received?
Oh no, I've only just looked at it this afternoon.
All right, yeah. Fair enough. And we will see that. I think your teacher's strategy is just to ask students repeatedly doing the exercise. Hopefully, at the end of the day, they will at least remember, part of it or all of it, hopefully. Where are we now? We got UAB intent. Yeah, okay. Oh, electricity this time.
Yeah.
Okay, let's go to whiteboard.
And there's only 10.
You only 10, okay. We can do it one by one, no problem. Do you want to try first? Do you want to try if you could solve this problem? Because eventually, I hope you become independent, okay? Number 1.
Okay.
Current.
Oh.
Okay, yes, you can open the formula there to see which formula can help you. Just stop that one.
I've never done one with time in it.
Time in minute, right? So that's something you need to come to. That is not international system. Is this time? So can we say that's given condition? So this is a given condition. You got the time first. Time is 30 minutes, right? So in that way, you needed to convert that into the second. How to do that? So
divide by.
Well, basically, we know that 1 minute equal to how many seconds?
1 minute. 60.
Yes, that's easy, right? So that's
so we just divide it by 60.
I tell you what, not divide, not divide. Let me help you.
I mean
30
times.
Time, yes. It's totally different, you see. If I write this down, can we say write 1 minute? Can we say 1 minute here? I rewrite this formula in this case, okay? And then I substitute this result here. Can you see? I just substitute that, right? If you look here, you look at screen, and that would be 60 seconds. Can you see? That automatically done. Then
Yeah.
that will be 30 time, not divide 60. And then I will put this second behind, okay? After do the conversion, we just obtain the time unit in the international system. Okay, that's the first thing to do. So basically they're dealing with what are other given condition? Can you look at that?
Amps.
Yeah. What is a current? What is the notation for current? Can you check my formula? What is go to electricity part? What is notation for current?
Oh, A. I mean I.
I. So what is the formula for current? Look, can you see there is a Q divided I? So Q divided by T.
Yep.
Yep, that is formula. That's formula to go.
Oh.
Okay, I think that will let's give you a shortcut, okay? That will help you to solve this problem. So where are the formulas? I have to open again.
That makes sense.
Okay, now this is step one though. This is step one. How about next? What shall you do next?
I need to rearrange it.
Yes, you need to, what is unknown in this case? What is unknown?
The Q is unknown.
Q is unknown, that's right. So therefore, do you want to try how to rearrange that?
Yeah, I can give it a go.
Yep.
Can I just tell you though, so that you can write it so it doesn't get messy on your screen?
Oh, not the matter. It doesn't matter. This is not whole. This is just the you know, as
I need it. Is it
what you to obtain
I times Q?
I times Q? Yes, I times T.
I times T.
Yeah, times T. So this is formula, right? To obtain the formula, can we times T on both sides? This is something you need to.
Oh yeah.
That's how to manipulate the formula, okay? In doing so, we canceled this T, can you see? That's our purpose. This is just like play the game, that's the trick. We need to find the Q alone on one side of equation. So therefore, we can say the Q will equal to I times T, right? Or just say IT. So we got I, can we list the current I? What is I? Given current condition is current is given, I remember.
2.5.
2.5 unit, please.
A.
Amp, it's called amp.
Amp.
Now, can you look at amp? Can you look at my page here, looking for the unit of the current? If you look at a single page, first page. A is initial for ampere. Ampere is a French physicist, actually mathematician as well.
Okay.
So that is just M. Okay. Now we got everything in international system. What can we do next? We just plug everything in. Okay. Plug everything in. Do you want to try, or do you have writing pad, or you don't?
Oh yeah, I do it on here.
Yeah. Do you want to try? Oh, you want here? Okay. But I can't see you, right? If you try this screen, I know if you know how to do it or not. You see.
Oh, I need to put my annotate tool on.
It's too small.
Or... Oh no, I got it.
Okay. So we get this result will be 1800. Yeah. Okay, that is numbers. It's large number, right?
Mm-hmm.
Now that is what is the unit for Q in international system? It's huge number, right? 4,000 something. Yeah. The question is, what is the unit, please? What is the unit here?
C?
Yeah, C for what?
Coulomb?
That's right, C for Coulomb. Okay, that's in one way. But however, well, the question is not using this unit. They use the asking different. They ask how many electron, right? I'll go back here. What is the question? So they say how many electrons are moving through this circuit each second. Now, this is a quantity of charge. Now you have to count the number of the charge, number of the electron. How do we do that? As I say, any charge will equal to the multiple times the E. Do you know this formula? So N is a multiple, N is just number. So N is a number. So N is a number. This is the number of electron. Right?
Mm-hmm.
So this is formula 1, this is formula 2. So sometimes you need 2 formula. I hope I will incorporate this formula in the sheet, right? Next time you will use that. So we got a Q.
Where is that one?
We don't have, probably I didn't put that one, not yet. But you just consider that as a new formula, that's fine. You see,
Okay.
the charge is can be counted, you see. It's very interesting that electrical charge can count in the unit of electron. No matter how much the charge is, you can always use this formula to count how many electrons there, number of electrons. Of course, there are many number of them. Now, to use this formula, we need to find a formula for N. Do you know how to rewrite this formula in order to calculate N? So N is unknown. So N is unknown, number of electrons. You multiply, you divide.
You have to divide the
E
on
for
both
electron.
sides.
Okay, good. We got E, so we got Q divided by E equal to N, right? So therefore, we got what we want. The formula for number in question will equal to Q divided by E. But what is E in Coulomb? Look at your formula, second page. If I write into a scientific notation, that will be 4.5 times 10 to power 3. 1.6, 1.602. Can you check?
Is it on the second page?
Second page, yes. The constant.
1.602 times 10 to the power of negative 19.
That's right. That's unique. That is what you needed to do. You need to use as a 10 to power 9.
Wait, how did you get 4.5 times 10 to the power?
I'll just rewrite this formula. Can you see here? This is 4,000. Is that 4,500? Is this 400?
Yeah.
Yeah. So that's using scientific notation. You can rewrite that as 4.5 times 1,000. 1,000.
Say if in the exam I didn't change it, does it matter? Will I still get the same answer if I just left it as the 4,000?
Yeah, you get a correct answer. But in our case, we need to calculate this number now because with this scientific notation, that can be easily done. Okay. Now, can you work out this number? I suggest you, before you go to calculator, I suggest you use calculator to calculate this only. So 4.5 divided by 1.602, okay? The rest is simple. The rest would be 10 to 19 plus 3, or 20, that will equal to 22, right? So what is this number? What is this number?
Which one?
4.5 divided by 1.6.
It is 2.8089887764.
Approximately 2.8, right? Approximately, right?
Yeah.
So how about the this? So do you know how to work out this now? 10 to power 19 plus 3 will be 22. Can you see?
Yeah.
Now that's the answer. I can see one of the answer is ours. Can you see that? Go back to the question, please. Question 1, A, B, C, D. Can you see that, page 1?
Yeah,
That's a huge number, isn't it?
it's the bottom.
Yeah, number D. So the D is correct. So you choose D.
Ah.
Is that fun? So you are dealing with some very invisible, tiny particle. Still, scientists have actually measured this small amount of charge precisely. So that is why as students, you can just borrow, you can just use these numbers in order to solve the problem. Okay?
Yeah.
So in this question, two important formula, I just highlight that two important formula are, one is what is current, okay? And another is how to count the number of electrons. These two formula are used. Okay. Can we go to next question? Any question?
Yeah. No, I think I get it.
Good. Okay, that's electricity. Oh, that electricity again.
I think this whole worksheet's on electricity.
Oh, okay. All right. Well, we can focus on electricity today. Do you want to try?
Calculate the magnitude of V2 in the following circuit.
Yeah. Do you want to try first? So number 2. If the front is too small, let me know. I can write a larger one. Number 2. Yeah, the circuit. How many resistors there? They got 2 resistors, right? But do we know resistors? Calculate the magnitude V2 in the following circuit. Aha, we don't know resistor, but we know one of the voltage drop at V1. So what is the relation of the individual voltage drop with the voltage of the battery? So if you have resistor like this one, I probably redraw your diagram. So that one. So if you put a battery here, if you put a battery here, probably that's more than one. That's enough. I just redraw this diagram. So the voltage is created by battery is 21, right? The total voltage drop is 21. That is created by the battery. Then the voltage drop in these 2 resistors are V1 and V2 respectively. If I use the diagram, you will know what I mean. So the voltage is a current like water. So the battery just raises the potential. So from this side, the potential will increase, right? And then when they arrive the battery resistors, they will drop a little bit, okay? And then continue move because there's no resistance. Whenever there's resistance, the voltage will drop, okay? So when they encounter second resistors, the voltage will drop. The lowest voltage will be equal to this side. So on this side, so the voltage here, can I use different color? So if the green is a negative, so this voltage will equal to the voltage here, right? Similarly, the voltage on the positive will equal to the voltage here, right? So that is, if you use this is a voltage, there's a voltage here. However, the voltage after one resistance will change. So after one resistance, that will be the voltage after passes another first resistors. Can you see this mountain? So this is like a mountain, right?
Yeah.
So based up the battery help electricity, help the charge go uphill, okay, uphill. However, the resistors just force these charges slow down. So therefore, every time they will drop. So therefore, if you use this, vertical, this is our voltage this is a voltage here. The voltage of the battery will equal to the sum of the voltage drop across to the resistor in series. Can you understand?
Yeah.
So the electrical charge is the electron, so the current will go that direction. So electrical current will go from positive. So this is how the electrical current go. So this is how electrical current go, right? Whenever they encounter the resistance, their voltage will drop. I think we still have to write the Ohm's law here. Do you know Ohm's law? Current equal to voltage divided by R. You know this one?
Oh, so formula.
This is Ohm's law. I'm not sure if I encode that into the formula sheet.
I think you did.
Yeah, I did.
Yep, you did.
Oh, good. So that is
You
important.
just did it the other way around.
Ah, at V right to R times I, right? Yeah.
Yeah.
They're equivalent. That's right.
Yeah.
So what does Ohm law say is that whenever there's a resistance, the voltage will drop. Okay? But the total drop must be equal to the voltage rise created by battery. Does that make sense?
Yeah.
So you just because you got your voltage, the voltage is high, you can just easily go downward, okay? Downward. And then always go downward. But of course, at the end, you will reach to the lowest voltage. Then the charge must be bring by the battery from negative side to the positive side. And that loop, this just continue. So that current just move continuously. Now the question, how about if there's more than one, there are more than two, how about this case? If we got 3, oh, before we go further, can you solve the problem now by using this formula here? Do you want to try?
The V1, V2.
Yep. So in this case, in the question 2, what is given, what is unknown? So basically, the given condition is so given V, the total voltage is 21 volt. Okay, not 21 volt. Okay, so this unit, and the part of the drops is given. It is 7 volt.
7.
Okay? And is unknown. What is unknown? So basically, V2 is unknown. So what, do you know the question now? So what can we know? What can we do?
It's V minus V1 to equal V2.
That's right. So therefore, because V equal to V1 plus V2, so therefore, V2 will equal to V minus V1. Can you plug in your numbers here? You got 21 minus what? 7?
14.
Yeah, oh, got 14. What's the unit? What is the unit?
V.
No.
Oh.
Unit. Volt.
Oh,
Volt. Can you look at the formula? That's called the volt. That's the unit, full name. V is the initial. This is the volt. The volt. So how to read that? You say V2 equal to 14 volt. That would be the answer. That is unknown. Now, do you want to compare with result?
Yeah.
That's B, right? That's B.
Yeah.
Good. We have made some progress now. Can we go to number 3? Oh, this is a bit complicated. Got 3. Calculate the power dissipated in R3. So this is a part of the circuit, right? Do you agree? This is just part. This is an incomplete diagram, but it's part of that. But fortunately, we can use meters to measure the current and the voltage drop, both. Okay. At school, did you do any experiment in the classroom?
I mean, we probably did, but I can't remember now.
Oh, do you know how to measure the current and the voltage? No?
With a machine.
Oh, just meters. nowadays very small. Is I can show you something. Can you see my? Can you see this stuff here?
Yeah, we have one of them at school.
That is old fashioned, but it's very useful. If you want to measure the voltage, you just use these two pins, okay, to connect which side. For example, you will connect the both end of the resistors. So in that way, you can measure the current and the voltage. That is how people use this tool before. Anyway, return to the question. What is the condition? So what is the condition given here is two, right? One is R3, this R3. The resistance is given. That equals 500 ohm. It's just ohm. The whole name is just ohm. Yeah, the Greek name is omega. Yeah, do you know the watch, Swiss watch? The tennis player often do this advertising. That is omega. But you read that ohm here. Now, what is the current? What is the electrical current? It's a 300 mA.
300 mA.
So what does M mean? 1 M is, 1 just means minute, okay?
Minute.
Minute.
Oh, mini.
Minute, that just equal to 1 equal to 10 to power negative 3.
Yeah.
Like a millimeter, see, the millimeter. So this is a milliamp, the milliamp. So could you convert it into the amp first? Because in international system, we use amp for the current. Do you want to convert the 300 milliamp into amp?
Yeah. Is it? No.
Yeah, you just simply
can't remember.
Oh, I show you how I put it here. So how do you convert that? So can you write down here at this corner? So 300, can you see? 300 milliamp. Okay, what I do, I just rewrite this milliamp into, I don't touch the 300. I just rewrite this milliamp as 10 to power negative 3 amp. You see? Because whenever you say M, you will consider it as 10 to power 3. Do you know that if you say micro, if this is micro, then you will times the factor 10 to power negative 6. Can you see? That is a And also, of course, you know that if you say K, what does K mean? Kilogram. 10 to power. What is power index? In 10 to power kilometers. What does kilo? Number, I mean, what is number here? Should I put it 10 to power to what? Say 1 kilometer equal to how many meter? 1,000. How to write 1,000? How to write 1,000 in this index form? How many zero for 1,000?
3.
Yes, so I put 3 here. You see? So this is just some of example how to deal with this different unit. So then, can you simplify that? 300 times or 300 divided by 1,000. That's equivalent to 300 divided by 1,000. This time is divide. Can you work out the result? 300 divided by 1,000 must be a decimal, less than unit.
0.3.
0.3, what's the unit? What is the final unit now? What is the final unit now? We just convert the milliamp into amp. See, just convert.
Amp, so A?
Amp, yeah. A, capital A, that's right. Right, so that is a condition given. So that is I3. Because I notice that number just referred to the same resistors. So basically, if I measure that in old days, I just measure these 2 points, okay? I make these 2 points in order to find the voltage and the current. Now return to the question. What is the question? The power. Wow, that's the power is unknown. So what is formula for the power? Can you look back to the formula sheet?
For power.
Yeah.
The formula.
Yeah, electrical power for when we study electricity, what is the power?
Is it P equals IV?
That's one. Yeah, one formula. Yes.
P divided by WT.
Yes. Well, depending depending whether you know current or voltage, which one we know current. Which formula should we use? We know resistance. We know resistance, right?
So RI squared divided by V2R.
Now we only need, so the original formula, can I show you? Original formula is I times V, right? In this case, voltage is unknown. So we have used this formula to help. So we have to ask Ohm law to help. Can you see? That's where we should go. So therefore, if I rewrite this voltage, that will equal to R, so I times R, that will be equal to R square R. Can you see the formula there?
Wait, do I have to write? Is it I times R?
Yep, that's right. I times R, we could R, I squared times R. That is the formula I'm talking. Yeah.
Wait, can you rewrite that?
Rewrite what? Okay, rewrite.
Wait, so it's down the bottom here. You've got R.
Yep. So this I times R equal to I squared. That's why. I times R equal to I squared. Just check the.
Oh, okay.
Yeah, that makes sense. Now, can you plug the number now? Because we know current, we also know the R. So that is time to calculate the power in order to finish that multiple choice.
Wait, what's R?
R is resistance. R3.
We don't know that.
R3. They just put a number here just to remind you this is number 3. So can you consider this 1, 2, 3? They just put a label. It's just different resistors. So that
and then so it's 0.3 squared.
Doesn't matter. You just work out the number to see if you can match one of the choice, one of the 4 choices.
Times 500.
Formula.
I got A.
Yeah. Can you compare the result with the question itself?
45.
I mean, which choice? A, B, C, D. Which one do you choose?
A.
Oh, good. Exactly the same? Exactly the same?
Yeah.
But what is the unit? Be careful. What unit?
Watts.
Yep, that's watt. W. Yep. Good. That's good. Let's check if I just open your formula now. The internal, we go to electricity. Electricity, yep. So the formula for the volt. Yeah, perhaps you have look upward. The power is upward. Yeah, power is separate. Power equal to, yeah, that's right. We use the second formula, right? First formula is I times V. Second formula is R times I squared. The third one is V squared divided by R. Depend which one you know. Okay, seems to work. Okay, I hope we can repeatedly use this formula. Let's go to the question. Let's go to the question. Where are we now? Oh, here, number 10. Can we move to the next question?
Yeah.
Number 4. Aha, that is a potential difference is 1 volt. And is the same as 1 joule per coulomb. Oh, that's interesting. So you need to do some formula to work out that. Let's check if we have the formula for you in the single page formula. Aha, we didn't. So I will edit this formula for you, okay, next time. So to solve this problem, what I need you to know is this formula. I just go to new page before. So to solve this problem is number 3, question number 3. Number 3 now.
Yeah.
So is that to solve this problem, we need to know this. So the work done, W, will equal to Q times the voltage. This is voltage, is also called the potential difference. So V is called the voltage. Voltage. We got voltage, right? They have nickname is called the potential difference. Potential difference. Okay. So in other words, so this is a formula we have to. I will edit that into the formula sheet, but this is the formula we will start. We'll use this formula to start with. Now in this formula we have work done. We also got a Q. We got a V, right? So basically, these 3 have formulas. These 3 quantity have formulas. Can we just get? Can we just solve the Q first? How do we find the formula for Q? You divide, you multiply.
Divide it by.
Yeah, good. So work divided by V, right? Okay.
Yeah.
So the potential, say the potential is 1 volt. Or just if the Q equal to 1 volt, how about the unit for the just one volt? Will equal to what is unit for joule? Sorry, what is unit for work? As well for the energy.
W.
No, that is watt. That is for the that's for power.
Energy.
No. Can you go back to that? Can you go back to that formula? They have all. If you look for W, work done. So work done will be in unit of joule, right? Right?
It doesn't have work done, I don't.
Let me see. W. I should have W. Let's get again. They must have W here. Let's see. Can you go number 14? Can you go number 14? W.
Joules.
Joules, that's right. That's 1 joules, okay? I just use J for joule. How about unit for 1 volt? Voltage. Voltage is 1 volt, right?
Yeah.
It's 1 volt. Or perhaps we have to write the other way around. These ask for the potential difference. Oh, okay. Can we rearrange that formula here by just solve the voltage first, okay? How do we solve the formula for voltage? Do we divide or we?
Yeah.
You divide, yes. W divided by Q, right? Yeah, can we start from this formula here? So in this case, 1 voltage, that unit is a volt, okay? But also this unit can be written as a joule divided by, alternatively, 1 volt is also equal to 1 joule divided by 1 coulombs. Does that make sense? Because
so that's the formula of that.
So basically, you can either use a volt or you can use a J over C. Also, 1 volt, what does that mean? Is 1 volt is equal to 1 joule per coulombs. I write the full name for you. Perhaps this is something new for you. 1 joule per coulombs. Can you follow me? So this is interpretation of this formula from this one. I highlighted the formula we use here. So this is the formula we use. Okay. From this formula, 1 volt, we can tell that 1 volt will equal to 1 joules divided by 1 coulomb. Therefore, 1 volt is equivalent to 1 joule per coulomb. Or just say,
oh, so it's A.
Oh, it is A, yes. So sometimes you can see, sometimes the unit, for example, if you go to hertz, another thing we probably will encounter in the future is, can we go to look at the hertz? Can you go to formula 2022? Can you look at the formula 22?
Yep.
The unit is hertz. Did I use a bracket here? Is 1 hertz also equivalent to 1/1 second or per second?
Yeah.
So do you understand now? Sometimes 1 unit, the unit for 1 quantity can be written into more than 1 forms.
Yeah.
Okay, we should be able to solve another problem. How about number 5? Oh, electricity. Oh, mini diagram. Mini diagram. That is, can you see the 2 letters V and I? What do they represent?
Is this question 5?
5, yeah. They have 4 diagrams. You have 4 diagrams. And the vertical one is V. The horizontal is I. Can you tell me what do they represent? V and I. What is V? Voltage, yes, good. Or potential difference. Can you see? They got a nickname. You can either call the V the voltage or potential difference.
And then I is current?
It's electrical current. Yes, that's electrical current. So V is called the voltage or the potential difference, either way. Which graph best represents the relationship between the potential difference across a conductor and resulting current I through a conductor? Yeah.
Is it?
Which one? The first diagram says that the current, the voltage is constant,
straight.
right? It's constant.
Yeah.
So, yeah, that is one way. Because remember, if that equal to 0, if it's constant, that means something. There's no resistance. You agree? So that's very interesting question. It's number 5. Talk about number. So number 5 is this diagram. I draw the diagram properly. So to answer this question, you have to know. So in general, how about resistance? If there's just 2 scenarios. So this is let me see. This is a volt. This volt or potential difference. This is I. According to Ohm's law, we know that V equal to R times I. Do you remember? That is Ohm's law. That is Ohm's law. Do you agree?
Yeah.
So if R is resistance, then they should be the straight line. You agree? The straight line.
Yeah.
If there's R, okay, can we say that this is straight line here? Now, if the R increase, do you think this slope will increase or not? R is a slope. Can you see? If R increase, that will this slope will increase.
Yeah.
You understand? So therefore, because they are talking in this case, they are not talking about resistance. They are talking about conductor. For conductor, resistance is almost 0. So what would be the scenario? The resistance is almost 0. So R is extremely small. Okay, it's too small that you can actually consider it as almost 0, right? So this R equal to 0. This R equal to 0.
So it's B?
No.
I mean D?
No. Can you look at A instead?
So is the answer A?
Yeah, if that is depending how good the conductor is. If it's a very good or even a superconductor, you know superconductor?
No.
A superconductor has 0 resistance. Right?
Oh.
So, but number one is have trouble because according to Ohm's law, the current, when current is 0, the voltage will return to the 0. Can you see? If the current is 0, so therefore, if we choose A, we have trouble. Because why? Because the number one, the answer A says that you can just plug the current. No matter how big the current is, the voltage will be keep the constant, which is unlikely. So my choice would be number D, right? Would be the fourth. Because in this case, they didn't say exactly whether it's a superconductor or is a conductor with a certain amount of resistance. They didn't say. So the safe way to choose the answer is choose D. So we just assume the resistance is small, okay? Because this formula is consistent with this diagram. Actually, this diagram is consistent with this formula. This is how we use Ohm's law here.
Yeah.
All right, can we continue next time now? Let's save this part. Any question if you have anything unknown? So today we are talking about the potential difference. So don't worry, potential difference is just the same thing as voltage. So we have different name for the same quantity in physics. Why don't you spend some time get familiar with this formula we listed there, and we will see if that can help you to solve almost all questions in preparation in this book. I hope. No question?
No.
Okay. I will see you tomorrow, 5 at 5.
Yep.
Thursday. Did you save that? Did you save your side?
Yeah, I saved them. I saved them as we went.
Okay. Goodbye. Goodbye.
Thank you. Bye.
You're welcome. Goodbye.